Hello, y'all. Welcome to lesson 79 of my DP chemistry curriculum. Today we're going over reactivity 1.4.4. It's an HL topic. We are talking about as reactions approach equilibrium, delta G, or change in Gibbs energy, becomes less negative and finally reaches zero. We're going to perform calculations using the equation delta G equals delta G standard plus RTL and Q and its application to a system at equilibrium, as well as delta G standard equals negative RTL and K. So we're going to go ahead and talk about these equations. We're also starting to talk about equilibrium, which we're going to go into much more detail in our next unit. But for now, we're going to explain what equilibrium is and where we use it. So with most reactions, we look at them one way. Maybe you have some wood, and you burn it and you get some products like CO2 and H2O. Now, you can't get those back into wood. In these reactions, we think of them as unidirectional. We have some reactants and we have products. And it moves forward. That's what we mean with this arrow. The reaction progresses in a forward direction. But that's not true for all reactions. Sometimes we have reactions that move back. We have some that don't always stay in the forward or backwards reaction. You can kind of think of maybe like if you have a sealed container of water, you have your liquid water, and some of it evaporates into H2O gas, and that might recondense back into liquid. So we have H2O liquid turning into H2O gas, and some of that might go back into H2O liquid. So we don't actually use this arrow, we do a double half arrow. This shows that there is what we call a reversible reaction. We can progress forwards or backwards. And when those rates are the same, so when forward reaction rate is equivalent to reverse or backwards reaction rate, we call this whole thing equilibrium. So in like a sealed container of water, we constantly have water molecules becoming gas and those gas particles being reabsorbed back into the liquid. And we would say the gas and liquid state are in equilibrium. But this can happen in chemical reactions too. But let's look at one more physical reaction or physical change, one that's a little bit more obvious to see. You can do the same reaction with bromine. So bromine gas, or bromine is actually a liquid. It's one of our two elements on the periodic table that exists as a liquid. And in a sealed container, it has a very visible equilibrium as a gas. It starts rapidly becoming this like dark purple. So if we have a sealed flask with bromine liquid, you'll notice a dark haze start to form, and that is the bromine gas. And you actually notice that haze continue to form and get denser and denser, and eventually it'll stop getting dense. That stop getting dense represents the liquid and the gas turning into each other at equivalent rates. So what we're saying is the rate of Br2 liquid to Br2 gas is equivalent to that rate of Br2 gas turning into Br2 liquid. And this would represent the forward reaction. Oops. Forward reaction. And this would represent the reverse reaction. So I'm really trying to hit this home just because we're going to be using this terminology a lot in this video. So how do we actually quantify this? We quantify these values or the reaction So we quantify reactions at equilibrium with two things. K, sometimes referred to as Kc, and that is going to represent our equilibrium constant. But we also use Q, and this is our reaction quotient. So this is how we're going to quantify reactions at equilibrium. So we need a sample equilibrium reaction, A to the A plus B to the B reacts to form, and I'm just going to use white for that, C to the C plus D to the D. So if we are quantifying this equilibrium reaction, we can use either K or QC. Turns out K and Q are the same equation, which might make you ask, well, why do we learn them both? And there's a big difference. K is for reactions at equilibrium, and Q is for reactions not at equilibrium. However, we use the same equation, so I'm just going to say K is equal to Q, which is equal to the concentration, and I'm just going to try and use the same color scheme I used before. So I'm going to pre-make all my brackets, realize I didn't leave myself space. C, D, A, B, and the concentration of each of these raised to their coefficients. So you have to remember that we use square brackets to refer to concentration. And the lowercase refers to the coefficients. So K, or the reaction quotient, is equal to the product of the concentration of C to the C power to the times the concentration of D to the D power divided by the product of the concentration of A to the A power and the concentration of B to the B power. So one final thing we can do is we can realize this value will be greater than 1. So K is greater than 1 when we have more products. As products are on top, if our products is more, if we have more products overall, this value will be greater than this value, meaning K will be greater than 1. If K is less than 1, we have more reactants. So this tells us how an equation or how a reaction is favored at equilibrium. So if a reaction at equilibrium has more products, K is greater than 1. If a reaction at equilibrium has more reactants, K is less than 1. So this brings into the idea of Q. We can now relate Q and K. If Q is less than K, if Q is less than K, it means that the reaction will progress forward. We know that because the only situation in which Q is less than K is when we have a larger number on the bottom and a smaller number on top, meaning that we have to convert reactants into products to reach the K value. If Q is equal to K, then we know reaction is at equilibrium. And if our reaction quotient Q is greater than K, then reaction progresses backwards. The reverse reaction is favored. So this is how we use Q and K to determine or quantify our equilibrium reaction. So now let's integrate this into Gibbs energy. We said at the top that we're going to be using delta G and talking about that at an equilibrium process. So let's now bring back in Gibbs energy. So the first thing we're going to do is we're going to use Q to calculate energy, specifically, sorry, not just energy, Gibbs energy, Gibbs energy change. And because we're using Q to calculate Gibbs energy change when not at equilibrium. So we already had our original equation to calculate Gibbs energy change, but that was standard Gibbs energy change. So we before had delta G standard is equal to delta H standard minus T delta S standard. But we don't always have these values, and maybe we're not calculating the standard energy change. We're just calculating delta G. So we can instead use the equation. So I'm going to just cross this out because we're not using it right now. Delta G equals delta G standard plus RT ln Q. So what are these values? Well, we know delta G is our Gibbs energy change. That should be capitalized, apology. Gibbs energy change. And of course, our units are in kilojoules, mole, inverse. Our delta G standard is again standard Gibbs energy change. Gibbs energy change. And this is also kilojoules, mole, inverse. But what are these other weird values we got? Well, R we've seen before. This is a universal gas constant, staying at 8.31 joules Kelvin inverse mole inverse. And T is our absolute temperature. Absolute temp. And that's, of course, going to be in Kelvin. And then we have this funky thing right here, ln Q. This is the natural log of the reaction quotient. And this is going to be a unitless value, no units. So we can calculate our Gibbs energy change when not at equilibrium. This will help us determine whether a reaction is spontaneous or not, because we already discussed in our previous video, if this is less than 0, being negative, the reaction is spontaneous. If it's greater than 0, the reaction is non-spontaneous. We are left with another question. Well, how do we get our Gibbs standard? Well, it turns out we have another equation for that. So delta G standard is equal to negative RT ln K. So this uses, the only difference here is we're using the natural log of the equilibrium constant. Furthermore, we have a negative R value. So we can actually now do a little fun derivation of this. But before we do our fun derivation of these two equations, I will mention that both equations are found in your data booklet. So this equation's in your data booklet, and this equation is in your data booklet in that first section of equations, like section 1 or 2. But let's kind of talk about what these values actually mean. So this is our little aside here. As reactions progress, specifically reversible reactions, the composition of the mixture changes. What I mean is that we create more products and take away some reactants, or if we're doing the reverse, vice versa. But because this is changing, uh, so does so does Gibbs energy change. So, or I'm just going to use Gibbs energy. So as this reaction mixture is changing, the Gibbs energy will also constantly be changing. Equilibrium, on the other hand, when the mixtures are constant, is when entropy is maximum. So remember, entropy S is at its maximum at equilibrium. But furthermore, in addition, Gibbs energy change, ugh, I keep doing lowercase. So the change in Gibbs energy is at a minimum. So the Gibbs energy will be negative. The change in Gibbs energy is negative, showing a spontaneous reaction, but it will keep going that way until it reaches a true absolute minimum for Gibbs energy change. Um, and one last thing is we have to remember that at equilibrium, K equals Q. Our reaction constant is equal to our reaction quotient. Or sorry, equilibrium constant is equal to the reaction quotient. So let's keep all these thoughts in mind as we now will combine Gibbs equations. Again, I was going to lowercase. Gibbs equations. So let's take a look at delta G, but now instead of delta G standard, we're going to use our other equation, negative RT ln K. And we're going to add that to RT ln Q. Again, we are now going to be assuming equilibrium. So we'll come back to that in a minute. We can combine our natural log values, and what we're going to do is RT ln Q minus RT ln K is the same thing as saying, oops, RT ln Q over K. So now we're going to come back to assuming equilibrium. If K equals Q, therefore Q over K equals 1. Therefore, this becomes RT ln 1. But the natural log of 1 is equal to 0. Therefore, this is equal to 0. So this shows us that when we are at equilibrium, our Gibbs energy change is 0. This is expected. If we look at this graphically, and we look at Gibbs energy change, and we look at reaction progress, so we're going to have reactants, we're going to have products. Our delta G's are kind of at their maximum when we're on either side of reactions and products. But when we're at equilibrium, we have our minimum value. So right here at minimum value, this is where delta G is at equilibrium. So we have that minimum specifically when our K is equal to our Q, and we can even shift this one way or another. If our reaction favors our products, we might shift this minimum point over to the right. If our reaction favors our reactants, we might shift it over to the left. For now, I'm not shifting it at all. I'm just using it as a reference point here. And before we progress, I realized I actually made a small mistake here. I'm using delta G, but I should just be talking about regular Gibbs energy, not Gibbs energy change. We know that at equilibrium, delta G should be equivalent to 0, but I'm saying our actual Gibbs energy values are at their minimum, and we could compare even our reactants and products, saying that we don't really have much of a difference here, but at equilibrium, our G is at its minimum value. Minimum. So we'll do minimum G at equilibrium. All right. The last thing we're going to talk about is look at the relationship between our delta G and reaction, equilibrium constant. So if we look at our equation, delta G standard equals negative RT ln K. What we notice is that reactions are spontaneous. Reactions that are spontaneous have a delta G less than 0. Spontaneous also infers that we are moving forward. The reaction is progressing forward. Therefore, delta G less than 0 relates to a K that is greater than 1. A reaction that is spontaneous will progress forward naturally on its own, and therefore will have more products and reactants, creating a equilibrium constant value greater than 1. A reaction that is non-spontaneous will have a delta G, and these should be standard values, that is greater than 0. Therefore, our K value will be less than 1. So we can kind of relate our Gibbs energy change along with our equilibrium constant. As one goes up, the other is going to naturally go down. K will never be less than 0, or actually it will never be 0 either, but it will likely be a very low number to a very high negative exponent. With that said, I hope this helps you understand the relationship between delta G standard, K, and Q, and have a great day.